Welcome to The Debate. So, I want you to imagine you build a perfectly engineered bridge.
Okay, I'm picturing it.
Right. You know the exact tensile strength of every steel beam. You know the load-bearing capacity of, well, every concrete pillar. The math of classical physics tells you unequivocally exactly how much weight that structure can hold.
Mm-hmm.
It is a closed, perfectly deterministic equation. And honestly, it is comforting, you know?
Oh, it's very comforting. Yeah, the math gives you a definitive, closed answer, and physical reality obediently obeys that answer. It feels safe.
Right. But now, imagine a butterfly lands on the railing of that perfectly engineered bridge, and instead of holding steady, the entire structure instantly rips itself to shreds.
Wow, yeah.
That is the terrifying, sort of rule-breaking world of deterministic chaos. If you're listening to this and wondering how math can be both perfect and completely unpredictable, well, that is the paradox we are exploring today.
It really is.
We are dealing with systems entirely governed by exact mathematical laws. I mean, there are no random dice rolls here, yet their long-term behavior is utterly unpredictable. A microscopic change in the starting condition in tomorrow's stable system is suddenly unrecognizable.
It really is the ultimate paradox of dynamics. You know, the rules are absolutely rigid, but the outcome is completely wild.
Exactly. And that tension is the core of our discussion. We're examining a highly comprehensive academic paper that proposes something called the Complex System Response, or CSR, dynamic framework.
Right.
The authors of this paper have taken the incredibly rigorous mathematical proofs of chaos, proofs derived from ideal pure models like the scalar logistic map and the two-dimensional Henon map, and they have mapped them to estimable quadratic coefficients.
Which is a huge leap.
It is. So, the central disagreement we are tackling is this. Can we successfully translate these exact mathematical chaos certificates into an operational empirical framework to predict and control real-world complex systems?
Or, and this is where I stand, does the absolute mathematical strictness required to prove chaos make such applications practically impossible outside of a chalkboard?
Right. Well, I will be arguing that the CSR framework is a massive breakthrough. It successfully bridges static data to dynamic chaos, providing a validated, predictive tool that safely separates a system's underlying geometry from its dynamic behavior for real-world applications.
And I will be arguing that the mathematical strictness required for these chaos certificates, things like exact snapback repellers and complete dynamical closure, makes applying this framework to messy, open physical systems fundamentally fragile.
I see why you think that, but let me give you a different perspective on why this framework changes everything. Because for decades, chaos theory has been a beautiful but highly abstract concept.
Sure.
But this material does something genuinely revolutionary. It explicitly connects controllable inputs to an emergent property via a quadratic function and a recursive update law. Let's break that down.
Please do.
We are looking at exact mathematical landmarks. Take the scalar quadratic recursion, which is really just a mathematical way of describing a system that feeds back into itself over and over, like a population of rabbits growing and then competing for limited resources.
Classic example, yeah.
Thanks to this paper, we now have exact formulations for the very first period doubling flip at a discriminant of exactly delta equals 4.
Right, the moment the single population equilibrium splits into a 2-year oscillating cycle.
Exactly. It's like turning the dial on a dripping faucet, you know? At a precise point, a steady, single drip suddenly splits into a rhythm of 2 distinct alternating drips.
Mm-hmm.
And we have exact period 2 stability bounds for delta between 4 and 6. By translating these pure mathematical proofs into the CSR coefficient space, the framework allows experimentalists to actually estimate and measure that dial operationally.
Yeah, but
We aren't just theorizing about chaos anymore. We can pull the phenomenon of a period doubling cascade out of the theoretical ether and turn it into a testable empirical protocol.
Look, I'll admit, it is an incredibly elegant theoretical construct. The transition from pure topological proofs to parameter space is a masterclass in dynamical systems topology.
It really is.
For example, identifying transversal homoclinic orbits, or utilizing the precise Benedicts-Carlson binding and folding periods to track how fast errors grow along unstable pathways. It's beautiful. But we have to look closely at the hyperspecific parameter constraints this math demands.
Okay, like what?
Well, take the Henon map, which you mentioned. If you imagine stretching and folding a piece of dough over and over, that's the Henon map. It's a model of how things get chaotically mixed up.
Right.
But for the Benedicts-Carlson proofs to hold true on that dough, the parameter b, which represents the thickness or dissipation, must be extremely small. It implies a system that instantly loses almost all its energy at every step.
Well, sure, which is a specific constraint for that specific proof, yes.
But it speaks to a larger issue, namely dynamical closure. This entire framework relies on the assumption that every single variable required to determine the next state of the system is represented explicitly in your equations.
Yeah.
In a pure math model, you control the universe. In a real-world open physical environment, that kind of perfect isolation is a physical impossibility. Mathematical chaos certificates, like proving the exact point where a system maps perfectly onto itself, known as the R equals 4 full 10 conjugacy.
Yeah, the conjugacy.
Right. Those demand complete forward invariant regions. This means nothing can enter and nothing can leave. Biological and physical systems simply do not possess that.
Okay, but let's look at how the paper handles that reality, though. Because it doesn't just ignore the messiness of physics, it actively builds a tool to parse it out, specifically through the separation of geometry and gain. The CSR framework explicitly separates the system's response geometry from its local gain.
Ah, you mean the Hessian versus the Jacobian?
Precisely. The Hessian matrix represents the fundamental curvature and interaction of the components, the geometry. The Jacobian represents the immediate multiplier effect, the gain. Think of it like diagnosing a catastrophic car crash. Previously, if an engineered system went unstable, you just knew it crashed. But this framework allows you to prove mathematically why it crashed.
Right.
Was it because the fundamental shape of the road altered, meaning the Hessian geometry shifted underneath you? Or did the geometry remain perfectly stable, but the driver simply accelerated too fast on a straightaway, pushing the local gain beyond the threshold of stability? Being able to explicitly diagnose the mechanics of the failure is a massive leap forward for engineers.
I come at it from a different way. That separation of geometry and gain is theoretically beautiful, yes, but it is entirely contingent on the system actually being perfectly closed.
How so?
Let's stick with your car crash analogy. The human body, or a complex fluid dynamic system, isn't a paved road. It is an off-road mudslide.
A mudslide. Okay.
If your system is open, meaning an experimentalist misses even one hidden variable, or fails to account for a change in the weather, essentially, then your Hessian matrix, your geometry, becomes meaningless.
Wait, why meaningless? You are still measuring the local curvature.
Because the curvature you are measuring isn't the true underlying curvature of the system. It is a projection contaminated by unmodeled dynamics. You can't cleanly separate the road from the driver when the mud is constantly shifting underneath the tires.
Well,
You might think the road hasn't changed because your limited two-dimensional map says it hasn't, but you are failing to see the three-dimensional mountain pass you are actually driving through. If the system isn't truly closed, the mathematical distinction between geometry and gain collapses into operational noise.
that's an interesting point, though I would frame it differently. Because the framework doesn't just blindly assume you have mapped the whole mountain pass. It actively tests for it.
How?
The protocol relies on time-ordered transition data and out-of-sample prediction tests specifically to cross-validate the model. If there is a hidden state, a shifting mud patch you missed, the residual structure of your predictions will reveal it.
Will it, though?
Yes, the experimental transition data is used constructively to reject those hidden state alternatives. You fit the model on a complete set of trajectory data and you test it on data the model has never seen. If the geometry and gain separation holds up under cross-validation, you have operational mathematical proof that your set of variables is sufficient for the specific horizon you are trying to predict.
Okay, but sufficient for the horizon is exactly the phrase where pure math and applied engineering fundamentally part ways.
I don't think so.
If we are talking about issuing a true chaos certificate, we have to look at the actual mathematical mechanics required to prove it. The paper relies heavily on Morato's theorem, utilizing what is known as the snapback repeller.
Right, which is a brilliant piece of topology.
It is, but think about what it actually requires. A snapback repeller is a localized point in the system that is fundamentally unstable. All its mathematical eigenvalues exceed 1, which means it violently pushes everything away from it. To prove that true chaos exists, Morato showed you need a trajectory that wanders out into the vast wilderness of the phase space and eventually snaps back to land exactly on that repelling point. Imagine throwing a boomerang into a hurricane and needing it to land perfectly, flawlessly on the head of a pin.
That is a very dramatic way to phrase it.
But mathematically, that process implies an infinite time, perfectly precise intersection of variables. How on earth can an experimentalist observe such a highly sensitive, mathematically perfect, infinite time requirement in sparse, noisy, real-world data?
Wait, hold on. Before we get lost in infinite time boomerangs, this is exactly where the application saves the theory. We don't have to observe it over infinite time.
But
that is the specific genius of what the paper calls the finite time CSR deformation. The authors recognize that engineers do not have an infinite time, nor do they need it to make operational decisions.
But chaos is defined over infinite time.
Pure chaos is, but applied instability is not. By utilizing the finite time Lyapunov exponent, or FTLE field, much like the 12-step field used to organize finite time stretching in the Hanon map, the framework explicitly budgets expansion and contraction to specific, measurable coefficients.
Okay.
We can measure the local expansion over a set number of steps, say 12 steps. So I have to push back on your premise here. Why demand infinite time topological proofs when a robust, positive largest Lyapunov exponent over a declared finite horizon is mathematically sufficient?
Because it's a completely different standard of proof.
It acts like a giant check engine light for an engineer. If the FTLE is positive, the system is locally tearing itself apart right now. In the real world, whether it happens over 12 steps or infinity doesn't matter if the bridge collapses on step 6.
I'm sorry, but I just don't buy that. Let me tell you why.
Go ahead.
A positive finite time Lyapunov exponent does not guarantee sustained chaotic dynamics. It merely guarantees transient temporary amplification. And this is where the mathematics of this very paper actively warns us about the extreme dangers of relying on finite time observations.
You are referring to the boundaries.
Yes, specifically the Shu-Yu theorem cited in the material regarding the period 3 boundary at delta equals 8. The theorem proves the exact coexistence of two completely different realities at the exact same parameters.
Right. You have regular attracting periodic motion existing simultaneously with a chaotic invariant set. Think of it like a massive, violent whirlpool hidden perfectly beneath the surface of a calm lake.
Okay, I like that analogy.
Because these two objects coexist, a finite time measurement, your 12 steps, might get temporarily trapped near the calm surface. The trajectory looks perfectly periodic. The engineer looks at the data and says it looks safe.
But an invariant Panter set of absolute chaos is silently lurking right there in the exact same phase space. A tiny perturbation, a single leaf dropping out of the water, pushes you off the safe path and you get sucked into the whirlpool. You cannot safely forecast transitions from sparse, finite time trajectories because that data is utterly blind to coexisting, lurking, chaotic structures.
I'm not convinced by that line of reasoning, because that coexistence is exactly why translating this into the CSR coefficient space is so valuable. It maps those whirlpools out for us.
Does it?
Yes. At delta equals 8, we have an attracting period 3 orbit coexisting with a chaotic invariant set. But because we have mapped this pure math into estimatable coefficients, we aren't flying blind in the lake. We know the math.
Assuming your map is perfect.
We know that if our fitted coefficients are approaching that delta equals 8 boundary, the system inherently possesses those latent chaotic structures, regardless of whether the current finite time trajectory looks smooth and stable. The mathematical certificate informs the empirical observation, It tells the experimentalist, your current trajectory looks safe today, but the underlying geometry of your response surface mathematically supports chaos. Be warned.
But that assumes your fitted quadratic surface perfectly matches the true global dynamics of the system. If your model of the lake is slightly off, you won't know the whirlpool is there until you are in it.
Well,
Which brings us to what is perhaps the most ambitious part of the paper, its application to real-world biology. Let's look at the paper's ultimate translational test, which is stability-aware personalized medicine.
yes, this is where the theoretical rubber truly meets the road.
The paper proposes a framework where you treat a patient's disease burden, their toxicity levels, and their immune status as state variables.
Right.
The idea is that clinicians can fit this quadratic CSR surface to a patient, compute the equilibrium multipliers, and prevent prescribing drug regimens whose predicted benefits are dynamically fragile.
And it is mechanically sound. It completely reframes how we think about dosing by indexing the patient's state over time and treating the drug dosage as the controllable parameter. The C vector in the CSR equation, the clinician can literally compute the Jacobian multiplier of the proposed treatment cycle. If that multiplier crosses what is called the unit circle, the math proves the treatment cycle is dynamically unstable. The patient's toxicity might oscillate wildly out of control, or the disease burden might suddenly escape the drug suppression.
Right, but
By separating the immediate response optimization, how good the drug works today, from the repeated cycle stability, you give doctors a mathematical tool to reject treatments that look good on day 1, but will cause chaotic physiological collapse on day 30.
That's a compelling argument, but have you considered the fundamental distinction between bounded dynamics and open flow transport?
I mean, yes, of course.
the paper itself makes this distinction perfectly clear. A bounded system, like the classical Hennon attractor, keeps typical trajectories confined in a compact region. But open systems require non-escaping invariant sets and chaotic saddles. The text points to spatial-temporal chaotic mixing in microfluidic channels as an example of open flow. A human patient is not a bounded, closed recursive loop. A patient is a radically open system.
But a microfluidic channel is an open system, and the math works there.
A microfluidic channel doesn't get a sudden fever.
Fair.
A patient is subject to massive parameter drift, sudden metabolic fluctuations, hormonal changes, and external forcing, like eating a grapefruit that alters drug absorption, that absolutely cannot be neatly augmented into a static quadratic state vector.
Okay.
You are taking idealized, invariant Cantor sets which are derived from proofs where parameter B is held strictly at a mathematical constant, and you are applying them to human physiology. It is a dangerous oversimplification of biological reality.
It would be dangerous if it claimed to be a crystal ball, but it doesn't.
It kinda does.
No, the framework does not claim to offer absolute infinite time prediction for a human patient. It explicitly positions itself as an uncertainty suppression tool. It acknowledges parameter drift. It acknowledges open flow dynamics. The clinician isn't trying to find a perfectly invariant, infinite time Cantor set in their patient's bloodstream.
Then what are they doing?
They are looking at the finite horizon uncertainty amplification. They are computing the finite time deformation tensor to see if the proposed drug regimen is going to violently stretch and fold the patient's physiological state into a chaotic domain over the next few cycles. It provides a falsifiable design principle. If the math shows the regimen is dynamically fragile, you just don't use it. It is a protective measure. It is a way to say no to bad protocols.
But if the system is open and the geometry is subject to unmodeled drift, that protective measure might give a false sense of security. Or conversely, it might cause a doctor to reject a perfectly viable treatment because a locally fitted Hessian implied an instability that the body's unmodeled homeostatic mechanisms would have naturally dampened.
But
The mathematics of Benedicts and Carlson relies on tracking unstable manifolds through incredibly deep mathematical folds. It demands precise knowledge of the binding periods to ensure the derivatives grow exponentially. In a patient, if your measurement of their state is off by even a tiny fraction, the modeled trajectory diverges from reality at an exponential rate.
sure.
The precision required to actually utilize these chaos certificates operationally is simply fundamentally at odds with the noisy, stochastic reality of clinical biology.
But that is exactly why the protocol includes rigorous exclusion tests. The experimentalist or the clinician doesn't just blindly trust the curve fit. They must test against measurement noise, surrogate data, parameter drift, and non-stationarity. The paper clearly states that the conclusion must match the supported level of evidence.
Right.
You only claim a validated invariant set certificate if you have the dense, repeated perturbation data to definitively prove it. Otherwise, you only claim finite time instability. The framework scales its claims to the quality of the empirical data, and that is why it is such a triumph.
I hear you.
It successfully pulls abstract chaos theory out of the realm of pure, untouchable mathematical topology. By grounding these complex phenomena like period doubling cascades and homoclinic tangles into estimable quadratic coefficients, we finally have a rigorous, testable protocol for identifying instability before it destroys a complex system, whether that system is an engineered bridge or a medical treatment plan.
Well, I will certainly affirm the immense analytical beauty of the proofs underlying this framework. I mean, the transition from Murado's abstract snapback repellers to the intricate Benedix-Carlson binding algorithms represents a true pinnacle of dynamical systems theory. Mathematically, it is absolutely gorgeous.
It is.
However, I maintain that demanding real-world empirical data to conform to these stringent, invariant set chaos certificates reveals a profound mismatch between theory and reality. Discrete deterministic mathematics relies on perfect closure, infinite timeframes, and absolute parameter stability. Noisy, open physical realities, especially biological ones, do not operate under those rules.
Yeah.
Assuming we can bridge that massive gap by simply fitting a quadratic Hessian risks masking the profound, uncontainable complexities of nature behind an elegant but ultimately fragile mathematical illusion.
And yet, without that mathematical framework, we are left completely blind to the mechanics of that complexity. Viewing chaos through both the lens of pure mathematical topology and applied empirical dynamics gives us a stereoscopic view of reality.
A stereoscopic view. I like that.
The complex system response framework opens up vast new avenues for exploring multivariable systems, giving us the tools to at least attempt to map the wilderness of chaos.
It certainly provides a beautiful map, but the listener will have to decide whether the mathematical bridge built from this theory can truly bear the immense, unpredictable weight of real-world complexity.
Just like building a bridge in the physical world, the math gives us the blueprints, but reality is the ultimate stress test.